Okay, hello physics students. We're going to look at a couple different examples out of chapter 8, which is all about rotational motion and rotational dynamics. I'll try to do this quick, so I kind of did the cheap version where I just photographed the book and we'll just go through the example from there. Okay? Alright, so first I just wanted to talk about, and I'm still learning some new software that I got here, so please be a little bit patient with me if you would. Try to get that thickness right there. Let's see if we can write. Yes, totally successful. Okay, so first I wanted to talk about the fact that when you're experiencing rotational motion about some kind of axis, your kinematic equations, you should know the kinematic equations from right here that you know so well, especially these three. Have their rotational versions. So there's a linear velocity. You now know that omega is rotational velocity. Initial velocity linear, initial velocity rotational, acceleration rotational, acceleration linear. Time is, of course, the same, or whether you're rotating or not. Remember that when we are moving linearly, our displacement is called like x. When we're moving rotationally, we're thinking about rotating through some kind of angle, right? So rotationally, we're thinking of like some kind of radius. And the distance that we're moving through, yes, this is an arc length, but basically the rotational distance, what matters is the angle that you go through theta. Okay, so theta is distance in rotational. I think all the other parts are pretty obvious though. So remember that we have those equations. I think we're going to need them as we look at this first example with a bike. Okay, I think I'm going to make this a little bit smaller. There we go. Now we have some room to write on the side. Okay, this one says a bicycle slows down. So its initial velocity, the bicycle is going about 8.4 meters per second. It takes 115 meters. That's not the time, that's the distance that it takes to slow down. I think that's a linear distance. So I'm going to give it a name and call it like x final, I think. So x initial, we'd just say is 0, of course. Each wheel and tire has an overall diameter. They give us the diameter. Oh, it's in centimeters. Better convert that. And it says define the angular velocity of the wheels when time is 0. So at the beginning, what is the angular velocity? So let's see if they did that. So the initial angular velocity. Well, one of those really essential equations that you should know is that velocity linearly is just a combination of angular velocity times radius. And remember, that just comes from thinking about arc length. That basically just comes from thinking about a little sector. I'll go ahead and rederive it for you real quick. Here's some kind of sector. Here's the angle. Here's the radius of that sector. And here's the arc length. I think the book called this L. I'm going to call it S. So a basic fundamental equation that the book did a really good job of deriving is that arc length is a product of r times how many radians you go through an angle. Okay, that comes from the definition of what a radian is. And remember, a radian is a unitless quantity. So if you want to get this velocity relationship, all you do is basically like take a derivative, really. So you write each with respect to time. So it's kind of like you divide by time on both sides. I'm going to write this as a derivative. If you take a derivative of s, you should know the derivative of position is velocity. R is kind of just like a constant here, and the derivative of theta is angular velocity. So that's one way to think about this, really. That's not the best way, but yeah, the book does a pretty good job of driving it another way. Anyway, this is a super fundamental equation. You don't want to forget it this year. We'll probably use it again. Anyway, so they asked for the initial angular velocity. That's the initial velocity divided by the radius. So you can see that they converted 0.68. 0.68 divided by 2 is going to be 0.34 meters for the radius here. Okay? Part B said calculate the total number of revolutions each wheel rotates through before coming to rest. I think that's just thinking about a wheel, and the outside of the wheel is the circumference, so that's 2 pi r. And it said that the total distance was 115. So dividing that by the time it takes to go around just once gives you the total number of rotations. So it looks like that's what they did. They stuck r in and they got, this wheel rotates 53.8 times. Okay? Part C, let's go back. Part C said the angular acceleration of the wheel. So angular acceleration, I think we have a nice little relationship for that too. I think it is the angular acceleration. Oh, maybe we don't have a nice little relationship for that. What was I going to say? Yeah, did we have one? I think the book, oh my gosh, my cat just caused a cat-tastrophe. Pun definitely intended. Aha, that's how I do it, right there. Let me put my cat away here. Come on, kitty. Everybody likes you, but I'm busy. Okay, back to where we were. So we were trying to find the angular acceleration of the wheel. And I was just going to take a quick look in the book. I thought we had a relationship for that, yeah. So we do, right? I think we do have a relationship for that. So I was thinking angular acceleration. Oh, let me get my pen. Let me get my pen. So angular acceleration, they use the variable alpha. You can get angular acceleration by taking the change in angular velocity over the change in time. That makes sense from calculus 2. Do we have both angular velocities though? We have the initial one. I don't think we have the final one. So we might have to use a kinematic equation here. We don't have both of them. So let's go back to our kinematic equations and see if we have anything. So we've got one angular velocity. So we could use maybe this. I don't know anything about the times involved though. But I think one of these kinematic equations is definitely the way to go. So you want to think about what you have and what you don't have. Oh, well. Where did they get that 24.7? Oh yeah, that's what we calculated here. So I was like, I don't recognize that number. But anyway, so I guess that was at the final. Excuse me. At the initial, we had 24.7, which we calculated. That's how many radians this rotation passes through per second. If you think about it, at the end, the angular rotation has to be 0 because the bike has stopped, right? It's going to stop rotating and then just put on the brakes right there. Okay. So we've got, I guess, the initial and the final. That's what I was a little bit confused about. So then you have that equation. So the kinematic equation, just like before, is that the end angular velocity, the end velocity equals the beginning or initial velocity. And I think it was plus 2a, which we're now writing as angular acceleration. And I think it was delta x. So now we kind of have delta theta because we're in angular land. So you just solve for alpha out of that. So I think that that is where they got this. They subtracted that guy to the other side, and they divided by 2 theta, or 2 delta theta. Okay, and we plug in our numbers. So 2 theta, and let's see, it looks like they converted that back to radians. Yeah, so they converted that number of revolutions back into radians. So I'd probably do that down here by myself. I don't like what they did. I'd probably say that that's revs. So I don't know why they even had us convert it in the first place. I think we're just converting back. So that is revolutions per second. I should get this out here. Sorry. Oh man, that's a big one. Let's see if I can fix this up. So that's revolutions per second. And we want to say that 1 revolution is how many radians? I think that 2 pi radians is 1 revolution. So that's what they've got up here. I don't like that. That freaks me out. So I would take that number to calculate delta theta first. That tells you how much angle you've gone through over those 53.8 revolutions, okay? So that's how much angle you've passed through. Obviously, it's a lot of angle. Anyway, you end up getting that the acceleration is negative, so that would probably just mean it's like turning counterclockwise at that fast, which makes sense. It's counterclockwise on this one if you're trying to brake, so it's experiencing that amount of negative deceleration, I should say. Totally makes sense. And then I think they said to find the time, so I think you can use another friendly kinematic equation. So like a kinematic equation is that velocity final is like initial velocity plus at, right? So in angular land, that's omega final equals omega initial plus angular acceleration times time, and you can solve for time. I think that's what they did. And they got that many seconds, okay? So there's one example. Let's go and look at some stuff with inertia. So I just wanted to go through one more time in case you didn't get it from the book and show you how to derive that. So let's extend this page and get some blank area here. So let me derive this. So we all know that force equals mass times acceleration, right? That's totally something that you're aware of at this point in the class. Okay, so what happens, may I ask, if instead of regular acceleration, you're experiencing acceleration that's angular in nature, so like you're going around in a circle, you're experiencing some kind of revolution, and you have an acceleration, you have your velocity vector that's moving like this, or your force vector, and you have an acceleration that is rotating. So in that case, I think that the tangential acceleration, based on the little vector stuff too right now, the tangential acceleration is going to be that times the radius, okay? You can definitely look at how they added their tangential acceleration. Sorry, it looks like that other video got cut off right in the middle. So we were looking at how to derive moment of inertia from Newton's second law, and we said that the acceleration in a linear sense becomes acceleration in an angular sense times the radius if you think about the combination of tangential and centripetal accelerations when you're moving in a circle and basically rotating. Okay, once you have that, I'm going to grab my smaller pen. So once you have that, I think that all that's left to do to create the moment of inertia is to kind of create the rest of this and turn it all into angular components. So forces, if you're working about in a rotational system, generally your force kind of becomes a torque, but you can't just make it a torque. Remember, if you remember, torque is a product of perpendicular, or should I say perpendicular or parallel? I think torque was perpendicular force times the lever arm R. So we need another R over here. So let's multiply both sides of the equation by an R. And I think you're allowed to do anything to both sides of an algebraic relationship so long as you do it to both sides. So now we have a force times a radius equals a mass times an r squared, and then we have how fast it's rotating, how fast it's accelerating angularly. This part becomes the torque, and in Newton's second law, I think we had a sum of the forces, so we've got a sum of the torques now. And here's basically the angular version of Newton's law. So in the angular version of Newton's law, Newton's second law, you can see that you have an equivalent to force. In angular land, the equivalent to force is torque, or the sum of the torques for the sum of the forces. And in angular land, you have an equivalent to acceleration. It's the angular acceleration right here, right? So angular acceleration. This part is obviously the equivalent to mass. So when you're rotating in a rotating situation, the equivalent to mass is called your moment of inertia. And that's what you guys are going to watch some of those calculus derivations to find, is you'll see that moment of inertia really depends on on both r and m. And it's totally different for different shapes, which you need calculus to derive what the moment of inertia is for different shapes. So I think we're just going to use it to solve a couple problems here. So there you go. There's the little derivation. Okay, so here's our first one. I don't think there's really a shape here. It just says you've got two weights, and they're stretched out along this bar here. Looks like they're an equal distance from the axis of rotation, so this must be rotating something like this, if you know what I mean. So in that case, I think each one is going to contribute the same amount to the overall moment of inertia in this system. So the overall moment of inertia in this system is created, remember we're imagining the system as just being composed of this mass and this mass, okay? I really have to learn how to get my lines to say small. Anyway, so moment of inertia is basically just going to be the sum of those little individual contributions of the individual masses. So the mass on the left contributes 5 kilograms, and its lever arm is like 2 squared. The mass on the right contributes a little bit more, 7 kilograms, and its lever arm is the same, so that's how much it gets. So you can see that the overall moment of inertia for this two-mass system is a little bit more influenced by the heavier mass in this case, and the overall moment is 48. You can see that the units here, of course, follow the fact that I, moment of inertia, is composed of a mass times a radius squared, kilogram meter squared. Okay, what if we change that and we say, you know what, we don't want to rotate over here. Now we want to rotate over here. And our masses are in a little bit different position this time. So this time we're going to think same relationship for moment of inertia, except the one on the left, the 5 guy, he doesn't contribute too much at the end of the day because his lever arm is so small, especially when you square it. The guy that's 7 has such a bigger lever arm that he contributes a huge amount more to the overall moment of inertia. I really like what they say down here. It says this example illustrates 2 important points. First, moment of inertia of a given system is different depending on where you rotate. When you change the axis of rotation and how the objects are rotating, you totally change how much inertia they create rotationally. And the second part is that the mass close to the axis, so if you have stuff closer to the axis, that's not going to create as much inertia as if you have something farther from the axis. Think about this. If you have this... Okay, so we're going to try this one more time. So I was talking about over here, so like if you tried to physically move this spot and rotate it, we had a rotational axis like this, right? So if you tried to rotate this element of this two-mass system and you tried to like rotate this guy that way, I think that would take a lot more effort. It would require a lot more than to rotate this guy. If you try to rotate this guy that way, it's going to be a lot easier than rotating this guy that's much farther away from the axis of rotation. I think so. If you think about that intuitively, the moment of inertia is just a way to describe that retardation of rotational motion that kind of occurs. So that's what the moment of inertia kind of measures, is the retardation of movement in a rotational sense. And I think that's also kind of what mass measures. If you have a greater mass, that means that you require a greater amount of force to be able to accelerate through a certain linear motion, okay? So let's look at one more example where we solve a problem like this. This time we have a pulley. I think they've given us a couple of specs on the pulley. They give us its mass, they give us its radius, and they say that looks like it's accelerating uniformly. So the kinematic equations that you're using, just like when they were linear kinematic equations, you have to experience a constant or a uniform acceleration, otherwise calculus would be involved and you couldn't use those equations. Okay, so same thing. This is stuff that'll let us get the angular acceleration. And sorry, my alphas are kind of bad. I guess I should do more like that. Okay. I've got the huge marker again. My computer just doesn't like me yet. I'm going to work with it though. Okay, it says there's also an external torque of friction. I think anytime you have a pulley or any kind of rope, you're going to have some kind of friction due to that kind of situation. So let's write Newton's second law down. I think that we have Newton's second law in a linear case is F equals ma. So in a rotational case, so I guess I'll put a sum here. That's going to be the sum of the torques is equal to the inertia times the angular acceleration. And I think what they wanted here is it says determine the moment of inertia. So I think what they want is that value for I. I'm going to go get a thinner version of my pen. Okay, so we're solving for I. So I is going to be the sum of the torques divided by angular acceleration. So I think we need to find both of those. So we were given that there's a frictional torque. The frictional torque is going to, of course, retard motion. So I think I'm going to say minus 1.1. Is that in the right units? Meters times newtons? Yeah, I think that's a torque. So minus 1.1. What other kind of torque do you have here just because of the motion of the pulley? So you can see up here too in the diagram, they show the frictional torque as going this way and the other due to the tension of the cord being wrapped around the pulley and actually pulling it. You can think of that as like an external force. These are opposite, so I'm going to say minus on that one, and the pulley itself is creating a torque of what? It's R times its force. Its force is going to be like mg, right? Or did it give us? Did it give us how many newtons there are or something? Oh, yeah, it did. I didn't even see this up here. I was getting a little bit lost. So we've got that that's going to be that external force times the big R minus the force of friction. There's our sum of our torques. And angular acceleration, well, they said angular speed, so they gave us omega is 30. They put it in radians per second, and they gave us in 3 seconds. So what is that? 30 divided by 3? I think it is. You could be really careful if you wanted and say omega final minus omega initial divided by your change in time if you wanted, so delta omega over delta t, but I think that that's the way this one works out. So what is that? 10 radians, I guess I can put my units in on this one, radians per second squared. We don't really need any of this stuff though. So we've got 15, we've got the radius on that guy is 33 centimeters, minus the friction they gave us, frictional torque, over our angular acceleration, and I think that should give us our moment of inertia. So let's see, I got, or I should say the book got, I'm lying, I didn't put it in my calculator, but the book got this. And it's moment of inertia, so I think it's mass times distance, or r squared. So there we go. So there we go. I think we've got that one. It says you can do a rough estimate of this by creating the moment of inertia for a uniform cylinder. So if you do like a uniform cylinder, I think you get something that's pretty close. But this isn't exactly just a cylinder. It's more than that. It's a pulley, so a little more complex. Okay, so hopefully I found this video useful. I'll try to make one more. Yeah, I might not get it done tonight, especially since my software keeps trying to go on the fritz. But there'll be another one soon. See you later.